Today we are going to discuss chemical reactions. So let's read from them. Difference in electronegativity between nitrogen and hydrogen atom and the presence of unshared pair of electron over nitrogen atoms makes amine react. The number of hydrogen atoms attached to nitrogen atom also decides the course of reaction of amines. That is why primary, secondary and tertiary amines differ in many reactions. Moreover, amines behave as nucleophile due to the presence of unshared electron pair. Some of the reactions of amine are described below. So first reaction is given basic character of amines. So let's discuss the basic character of amine. Amines are being basic in nature, react with acid to form salts. Here this is amine. As it is bonded to one alkyl group, this is primary amine. When it reacts with HX, it represents an acid. It abstracts H plus from the acid and forms ammonium salt. Here this is aniline. It is primary aromatic amine. When it reacts with HCl, it forms anilinium chloride. By the abstraction of H plus ion from HCl, it forms anilinium ion, and to balance the charge over anilinium ion, Cl negative ions get attached to it, and that's how anilinium chloride is formed. RNH3 positive X negative. This is amine salt when it is treated with OH negative ion. It represents base. So this base abstracts H plus from this amine salt and removes water molecule and regenerated alkyl amine, and X negative ions are removed. So that's how amine salts on treatment with base like NaOH regenerates the parent amine. Amine salts are soluble in water but insoluble in organic solvents like ether. This reaction is basis for the separation of amines from non-basic organic compounds insoluble in water. As the amine salts are polar in nature, they are ionic compounds, and all the polar and ionic compounds are soluble in water. That's why amine salts are soluble in water, while they are insoluble in organic solvents. The reaction of amines with mineral acid to form ammonium salt shows that they are basic in nature. Amines have unshared pair of electron on nitrogen, due to which they behave as Lewis base. Basic character of amines can be better understood in terms of their Kb and pKb value as explained below. So let's draw the structure of amine. This is nitrogen. It has lone pair of electron and it is bonded to two sides with hydrogen and one side with alkyl group. And due to presence of lone pair over nitrogen, these lone pairs can be donated to electron deficient species. So that's why it is a lone pair donor. Lone pair donor. Because it is a lone pair donor, it acts as a Lewis base. Lewis base are lone pair donor. Now let's write the reaction of amine with water. So this is RNH2. There is lone pair over nitrogen. When it reacts with water molecule, it undergoes dissociation. So here you will get RNH3 positive as nitrogen abstract H plus from the water molecule, or you can say water donated H plus to amine. As this amine accepts H plus from the water molecule, it will act as a Bronsted base. And after accepting H plus from the water molecule, it will form conjugate acid. And here, by the donation of H plus to amine, water will form OH negative ion, which is a conjugate base of water. As amines are weak base, they undergo incomplete dissociation. That's why there is an equilibrium. Now let's write the equilibrium constant for this equilibrium. So here you will get concentration of product. This is RNH3 positive multiplied by the concentration of OH negative ion divided by the concentration of reactant. which is R NH2 multiplied by the concentration of water. As here water acts as a reactant as well as a solvent. So the concentration of water will remain constant. So when you transfer this constant to the other side of the equation, here you will get K multiplied by the concentration of water will be equal to R NH3 positive multiplied by OH negative ion divided by the concentration of reactant, which is R NH2. So when you multiply one constant with the another constant, you will get the another constant. This constant is called as Kb, as this is the dissociation constant for the base. So here you will get the equation R NH3 positive multiplied by OH negative ion divided by the concentration of R NH. When you take negative log of Kb, so here minus log of Kb, this will be equal to pKb. From the equation, when you see, if the value of Kb is high, means there will be more product. More product means the base will release more OH negative ions. And for the higher value of Kb, pKb value will be lower. So let's read from the book. Larger the value of Kb or smaller the value of pKb, stronger is the base. The pKb value of few amines are given in table 9.3. pKb value of ammonia is 4.75. Aliphatic amines are stronger base than ammonia due to plus I effect of alkyl group, leading to high electron density on nitrogen atom. Their pKb value lies in the range of 3 to 4.2. On the other hand, aromatic amines are weaker than ammonia due to electron withdrawing nature of aryl group. So let's try to understand the meaning of these lines. In case of aliphatic amine, so here we are going to compare between aliphatic amine, aromatic amine and ammonia, means NH3. Aliphatic amine means R NH2. Aromatic amine means there is benzene ring to which NH2 group is bonded. So here aniline is one of the example of aromatic amine, and here this is NH3 ammonia. In case of aliphatic amine, alkyl group is bonded to nitrogen and nitrogen has a pair of electrons. This alkyl group donates electron density via plus I effect to nitrogen. That's how it increases the electron density over nitrogen. By the increase of electron density over nitrogen, these lone pairs will be more available for the donation. Now come to the aromatic amine. In aromatic amine, benzene ring is bonded to nitrogen and this benzene ring withdraw electron density from nitrogen. So that's how these lone pairs over nitrogen will be less available because they are involved in the resonance of the benzene. And in case of ammonia, there is no plus I effect. That's why ammonia is less basic than aliphatic amine and aromatic amine will be the least basic. So here you can summarize, aliphatic amine will be most basic among them and aromatic amine will be least basic among them. And ammonia comes in between aliphatic and aromatic amine. You may find some discrepancy while trying to interpret the Kb value of amines on the basis of plus I or minus I effect of the substituent present in amine. Besides inductive effect, there are other effects like solvation effect and steric hindrance, etc., which affect the basic strength of amine. Just ponder over. You may get the answer in the following paragraphs. Structure. Basicity relationship of amine. Basicity of amine is related to their structure. Basic character of an amine depends upon the ease of formation of cation by accepting a proton from the acid. More stable cations relative to the amine, more basic is the amine. So this concept is based on the conjugate acid-base theory of Bronsted Lawry. First comparison is given between alkenamine versus ammonia. So let us consider the reaction of alkenamine and ammonia with a proton to compare their basicity. This is alkylamine and there is ammonia. So first one is alkenamine and this is ammonia. When alkylamine abstract proton from the medium, it forms RNH3 positive ion. And when ammonia abstract proton from the molecule, it forms ammonium ion. Due to electron releasing nature of alkyl group, R pushes electron towards nitrogen, thus makes the unshared electron pair more available for sharing with the proton of the acid. Moreover, the substituted ammonium ion formed from the amine gets stabilized due to dispersion of positive charge by plus I effect of alkyl group. So let's try to understand the meaning of these lines. When alkenamine R NH2, there is lone pair over nitrogen, it reacts with proton H plus ion. This nitrogen abstract proton by the donation of lone pair to it. And here you will get equilibrium, you will get R NH3 positive. In alkenamine, the alkyl group bonded to nitrogen donates electron density via plus I effect. By the donation of electron density via plus I effect, the lone pair over nitrogen makes more available for the donation. So that's how it increases the basicity of amine. And as a result of it, RNH3 positive ions are formed. As this alkenamine accepts proton from the medium, it can be called as Bronsted base. And the cation formed by the exception of proton will be called as conjugate acid of alkenamine. Now check the stability of formed conjugate. So here, this nitrogen is electron deficient, and to fulfill the deficiency of this nitrogen, alkyl group is there, which donate electron density via plus I. That's how it stabilizes the formed conjugate acid. So this conjugate acid will be a stable conjugate acid. As the conjugate is stable, the base will be stronger and equilibrium shifted mostly towards the right side. Now come to the ammonia. So here this is NH3 and there is lone pair over nitrogen. When it reacts with proton of acid, there will be an equilibrium and here you will get NH4 positive. In case of ammonia, there is hydrogen which cannot donate electron density to nitrogen. So the availability of lone pair cannot be increased by the presence of hydrogen. And in case of ammonium ion, there is hydrogen which cannot donate electron density to fulfill the deficiency of nitrogen. So that's why this ammonium ion will be unstable as compared to the cation formed in case of alkenamine. So as this is unstable conjugate acid, so that's why the ammonia will be weaker base than alkenamine. Now let's read from the book. Moreover, the substituted ammonium ion formed from the amine gets stabilized due to the dispersal of positive charge by plus I effect of alkyl. Hence, alkenamines are a stronger base than ammonia. Thus, the basic nature of aliphatic amine should increase with the increase in the number of alkyl groups. This trend is followed in gaseous phase. Now let's try to understand it. Here it is written that the basic character of alkenamine increases with the increase in number of alkyl groups. So here it is written the basic nature of amine is directly proportional to the number of R groups. So here, when you increase the number of R group, here this is R, NH2. The next one is R, N, R, H, and here this is R, N, R, R. So here, as this nitrogen is bonded to one alkyl group, this is primary amine. As this nitrogen is bonded to two alkyl group, this is secondary amine. And this is tertiary amine. As nitrogen is bonded to three alkyl groups. In primary alkylamine, there is just one alkyl group which donate electron density to nitrogen via plus IA. In case of secondary alkylamine, there are two alkyl groups which donates electron density to nitrogen via plus IA. And there are three alkyl groups which donate electron density to nitrogen via plus IA. So in case of tertiary amine, the availability of lone pair over nitrogen for donation will be the maximum. That's why tertiary alkylamine will be more basic than the secondary amine, and secondary amine will be more basic than the primary amine. So in gaseous phase, these trends follow in the gaseous phase. The order of basicity of amine in gaseous phase follows the expected order. Tertiary amine is more basic than secondary amine, and secondary amine is more basic than primary amine, and ammonia is the least basic among them. This trend is not regular in aqueous phase as evident by their pKb value given in table 9.2. In the aqueous phase, substituted ammonium cations get stabilized not only by electron releasing effect of alkyl group, but also by the solvation with water molecule. Greater the size of ion, lesser will be the solvation, and less stabilized is the ion. The order of stability of ions are as follows. Here this is primary ammonium ion, this is secondary ammonium ion, and this is tertiary ammonium ion. Tertiary ammonium ion is the bigger one, and as it is written here, greater the size of ion, lesser will be the solvation. Means tertiary ammonium ion will be less solvated by the water molecules, and primary ammonium ion will be more solvated by the water molecules as they are smaller among them. So this is the decreasing order of extent of hydrogen bonding in water, the order of stability of ions by solvation. So primary ammonium ions will be more stabilized or more solvated than the secondary one, and tertiary alkyl ammonium ion will be the least solvated, means they are least stable. Greater is the stability of substituted ammonium cation. Stronger should be the corresponding amine as a base. Thus the order of basicity of aliphatic amine should be primary amine should be more basic than secondary than tertiary. As the cation formed by the primary amine gets stabilized by the solvation. That's why primary amine are expected to be more basic than the secondary amine, and tertiary amines are expected to be least basic among them in aqueous medium. And this trend is opposite to the inductive effect based order. Secondly, when the alkyl group is small like CH3, there is no steric hindrance to the hydrogen bonding. So there is another factor is introduced, steric hindrance. In case of alkyl group is bigger than CH3, there will be steric hindrance to hydrogen bonding. Therefore, the change of nature of alkyl group, for example, methyl to ethyl, result is change of the order of basic strength. Thus, there is a subtle interplay of inductive effect, solvation effect, and steric hindrance of alkyl group, which decides the basic strength of alkylamine in aqueous state. This is the order for the gaseous phase. Now we are going to discuss the order of basicity of amine in aqueous phase. In aqueous phase, first you have to consider inductive effect, second is solvation of conjugate acid cation, third is steric hindrance.
The order of basic strength in case of methyl substituted amines and ethyl substituted amines in aqueous solution is as follows. So first order is given for ethyl substituted amine. So when you observe it, here there are two alkyl groups bonded to nitrogen. So that's why this amine is secondary amine. Here there are three alkyl groups bonded to nitrogen. So that's why this is tertiary amine. And here there is one alkyl group bonded to nitrogen. So that's why this is primary amine and this is ammonia. So let's write down the order of basic strength in case of ethyl substituted amine. So here this is ethyl substituted amine. Now let's write down the order of basic strength. So here secondary amine is more basic than tertiary amine. Tertiary amine is more basic than primary amine, and this is ammonia. Now let's discuss all these amines with respect to stabilization by solvation, then inductive effect plus I effect, which increases the electron density over nitrogen, hence increases the basic strength. And the third factor is steric factor. Now let's examine each of them with respect to these points. Secondary amine is stabilized by the solvation, and there are two plus I effects, and there is less steric hindrance. So we can say it is less hindered. In case of ammonia, it is solvated, but there is no plus I effect. So there is no plus I effect, no steric hindrance. As there is no plus I effect, electron density over nitrogen is minimum among them. That's why ammonia is least basic among them. While in case of secondary amine, there are two plus I effect which increases the electron density over nitrogen, and the secondary amine is also moderately stabilized by the solvation, and it is less steric hindered as compared to tertiary amine. That's why you can say secondary ethyl substituted amine is the most basic among them, and ammonia is least basic among them. Now let's compare between tertiary and primary. In case of tertiary amine, it is not stabilized by the solvation, but there are three plus I effects. So the electron density over nitrogen is more as compared to primary alkylamine, and there is more steric hindrance. But due to the presence of 3 plus I effect, there is more electron density over nitrogen. Because of it, tertiary amine is more basic as compared to primary alkylamine. In case of primary alkylamine, it is stabilized by the solvation, but there is only 1 plus I effect, though it is less steric hindered. But because of less electron density over nitrogen, it is less basic as compared to tertiary amine. Now let's compare the basic strength of methyl substituted amine. So let's write down the methyl substituted amine. Methyl substituted amine. Here we are discussing the basic strength. Now let's copy down the basic strength for methyl substituted amine as it is given here. In methyl substituted amine, first one, here again 2 alkyl groups are bonded to nitrogen, so this is secondary amine. Here there is 1 alkyl group bonded to nitrogen, so this is primary amine. And here there are 3 alkyl groups bonded to nitrogen, so it is tertiary amine, and this is ammonia. So let's note down the order of basic strength. Secondary amine is most basic, then primary, then tertiary, and then ammonia. So the order of basic strength in case of methyl substituted and in case of ethyl substituted. In both the cases, secondary amine is the most basic among them and ammonia is least basic among them. There is change in the order of primary amine and tertiary amine. In case of ethyl substituted amine, tertiary amine is more basic as compared to primary amine, while in case of methyl substituted amine, primary amine is more basic as compared to tertiary amine. So let's try to understand why there is change in order of primary and tertiary amine in case of methyl substituted amine. In case of methyl substituted amine, primary amine is more stabilized. It is stabilized by the solvation. It is stabilized and there is one plus I effect and it is less sterically hindered. So we can write here less hindered. While in case of tertiary alkylamine is less stabilized by the solvation. There are 3 plus I effects and it is more hindered. So when you compare the basic strength of ethyl substituted and methyl substituted amine, in case of ethyl substituted amine, plus I effect dominate over the other effects. That's why tertiary ethyl substituted amine is more basic as compared to primary ethyl substituted amine. While in case of methyl substituted amine, there is solvation and steric hindrance outplay the inductive effect. So that's why primary alkylamine is more basic as compared to tertiary alkylamine in case of methyl substituted. When you compare the plus I effect of ethyl and methyl, so here I can write bigger the alkyl group, stronger the plus I effect. Bigger alkyl group has stronger plus I effect. That's why in case of ethyl substituted amine, plus I effect dominate over the other effects, while in case of methyl substituted amine, other effects dominate over plus I effect. Now let's read from the book. Arylamine versus ammonia. pKb value of aniline is quite high. Why is it so? It is because in aniline or other arylamines, the NH2 group is attached directly to the benzene ring. It results in the unshared pair of electrons on nitrogen atom to be in conjugation with the benzene ring and thus making it less available for the protonation. If you write different resonating structures of aniline, you will find that aniline is a resonance hybrid of the following 5 structures. So let's draw the resonating structure for aniline. So here this is benzene ring. When NH2 group is bonded to benzene is called aniline. So here this is benzene and this is NH2. Nitrogen has a pair of electrons. These pair of electrons participate in the resonance of benzene. So these lone pairs shift between nitrogen and carbon and this pi bond move to the next carbon. So here you will get the another resonating structure. Here this is benzene. These two bonds remain same and here there is double bond is formed between nitrogen and carbon NH2. Because of the donation of lone pair to benzene, nitrogen develops positive charge. and as this pi bond moves to the carbon, this carbon develops negative charge. Now in the another resonating structure, this negative charge moves between these two carbons and the pi bond moves to the next carbon. So here you will get the next resonating structure. In this structure, this bond and this double bond remain as it is. So this is NH2. Nitrogen has positive charge. As this negative charge moves between these two carbon, new bond is formed between these two carbon. As this pi bond moves to the carbon, this carbon develops negative charge. Now you will get the another resonating structure in which this negative charge moves between these two carbons and the pi bond moves to the next carbon. So here you will get, this is benzene. This bond, double bonds remain as it is, NH2, and nitrogen has positive charge. As this negative charge moves between these two carbons, new pi bond will form here and negative charge move to this carbon. Now you will get the another resonating structure. As this negative charge moves between these two carbon, this pi bond again move to the, so here you will get another resonating structure. In this resonating structure, these two pi bonds will remain as it is. Now new pi bond is formed between these two carbon and bond between nitrogen and carbon again becomes single and the positive charge over nitrogen neutralizes. So here in these resonating structures you can observe, in most of the resonating structure, nitrogen is devoid of the electron. Nitrogen has positive charge, means the lone pair of nitrogen are involved in the resonance of the benzene ring. So that's why the lone pair over nitrogen is less available for the donation, or you can say in the other word for the protonation. That's why aniline is less basic as compared to ammonia. Now let's read from the book. On the other hand, anilinium ion obtained by accepting a proton can have only two resonating structures. Now let's write the equation when aniline donate a pair of electron to proton. So this is benzene. It is bonded to NH2, so it becomes aniline. Now when this aniline react with protons, so nitrogen donate a pair of electron to proton and accept it, and thus it forms anilinium ion. So this is benzene. After donating a pair of electron to proton, nitrogen will develop positive charge and here you will get NH3 positive. This was aniline. So it becomes anilinium ion. Now let's check the stability of anilinium ion. Now let's draw the anilinium ion. So this is benzene. Here NH3 and nitrogen has the positive charge. When you draw the another resonating structure, you will see this pi bond move between these two carbon and this it moved to here and like this. Now let's draw the another resonating structure. So here you will get, this is benzene. Now you will see pi bonds are moved to different position. So here and here this is nitrogen NH3 positive ion. So you will see there are only two resonating structures in case of anilinium ion. Means aniline is more stable as compared to anilinium ion. So that's why equilibrium will shift it mostly towards the left side. Means it do not favor the donation of lone pair to proton. That's why aniline is less basic as compared to ammonia. Now let's read from the book. We know that the greater number of resonating structure, greater is the stability. Thus you can infer that aniline 5 resonating structure is more stable than anilinium ion. Hence the proton acceptability or the basic nature of aniline or the other aromatic amine would be less than that of ammonia. in case of substituted aniline, it is observed that electron releasing groups like OCH3 or CH3 increases basic strength, whereas electron withdrawing groups like NO2, SO3H, COOH or X decreases it. Now let's try to understand it. In case of electron releasing groups, so this is benzene. It is bonded to NH2. So this is aniline. In case of aniline, if electron donating groups are bonded to ortho or para positions. This is electron donating group. So when they are bonded to ortho or para position, this electron donating group increases the electron density over nitrogen by plus I effect and plus M effect. Hence increases the availability of lone pair over nitrogen for the donation. That's how they increases the basic strength. So that's why they increases the basic strength. While in case of electron withdrawing groups, so let's draw the structure of aniline first. So this is benzene, it is bonded to NH2 and nitrogen has a pair of electrons. So this is aniline. If it is bonded to electron withdrawing groups, to ortho and para. If electron withdrawing groups are bonded to ortho or para position, they will withdraw electron density by minus I or minus M effect. Hence they decreases the availability of lone pair over nitrogen for the donation. So that's how they decreases basic strength. Of aniline. Now let's try to solve the question given here. Example 9.4. Arrange the following in decreasing order of their basic strength. First one is aniline, second is ethylamine, third one is diethylamine, and the fourth one is ammonia. First of all, draw the structure of these amines. So first one is aniline. Here this is benzene bonded to NH2. This is aniline. Second structure is ethylamine, C2H5 NH2. Next one is diethylamine. This is C2H5NH and it is whole twice. And the fourth one is ammonia, NH3. So we know aromatic amines are least basic. Now we have to write the order in decreasing order. So we know in case of ethylamine, secondary amine is more basic among them. So here first we will write C2H5 whole twice NH, because ethyl substituted amine there are 2 plus I effects. So 2 plus I effect, it is stabilized by the solvation and it is less hindered. So it is less hindered. So that's why secondary ethyl substituted amine will be most basic among them. It will be most basic among them. Then primary ethyl substituted amine will be there, C2H5NH2. Then there will be ammonia, NH3, and then there will be aniline. So this is benzene bonded to NH2. So this is the decreasing order of basic strength of following amines. In the next video we will discuss the other reactions of alkylamines.